Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, India. Today we are going to discuss about the module Atomic Force Microscopy Part 2 comes under the unit Surface Morphology from the paper Characterization of Materials 2. So, students, let us see what we are going to learn in this module. First, we will review the basics of AFM that we learned in the last module. We will learn about the operating modes in AFM, and we will see the various kinds of force microscopes available. The atomic force microscopy includes various methods for detecting the interaction of probe and the specimen that helps to characterize various material properties. In this context, AFM can characterize mechanical, electrical, magnetic and optical spectroscopic properties. In this article, I will explain in detail the different modes of operation in AFM and kinds of AFM systems. Different modes of operation in AFM. First is the contact mode AFM. It works at a probe surface separation of less than 0.5 nanometer. Second one is the intermittent contact or tapping mode. It works at a probe surface separation of 0.5 to 2 nanometer. Third one is the non-contact AFM mode. It works at a probe surface separation of 0.1 to 10 nanometer. The three modes are sketched in figure 1 and the variations are tabulated in table 1. The contact mode AFM. In this mode, the AFM tip is gently in contact with the surface of sample and records the small force between the probe and the surface. The cantilever is held at a distance less than few angstroms away from the surface of the sample. This mode operates in the repulsive regime of the van der Waals curve, that is, the force on the tip is repulsive. When the spring constant of cantilever is less compared to the surface, that is lower than effective spring constant that binds the atoms of the sample together, the cantilever bending occurs. With a constant cantilever deflection using a feedback loop, the force between the probe and the sample is maintained constant and an image of the surface is obtained. In the contact AFM mode, the tip makes soft physical contact with the surface of the sample. Here, the deflection of the cantilever, which is dx, is proportional to the force acting on the tip via Hooke's law, which is F is equal to minus k dot x, where k is the spring constant of the cantilever. In contact mode, the tip either scans at a constant small height above the surface or under the conditions of constant force. In the constant height mode, the height of the tip is fixed, whereas the constant force mode, the deflection of the cantilever is fixed, and the motion of the scanner in the direction of height z is recorded. By using contact mode AFM, the atomic resolution images could be captured. The constant force. In constant force mode, the deflection of the cantilever can be used as input to a feedback circuit that scans up and down in z direction and responds to the topography by keeping the cantilever deflection constant. With the cantilever deflection held constant, the total force applied to the sample is constant. The motion of the scanner in the z direction helps generating images of the sample surface. The scanning speed is thus limited by the response time of the feedback circuit. Constant 4 mode is generally preferred for most applications. Intermittent or tapping mode. For imaging biological samples, the constant force that the cantilever exerts on the sample in contact mode is quite large. In such cases, it is advantageous to work in dynamic mode, also called tapping mode or intermittent contact mode. In this mode, the cantilever oscillates with an external piezo close to its resonant frequency as shown in figure 2. The probe lightly taps on this sample surface during scanning and contacts the surface at the bottom of its swing. By maintaining constant oscillation amplitude of 20 to 100 nanometer during scanning through an electronic feedback loop, a constant tip sample interaction is achieved and an image of the surface is captured. Forces that act between the sample and tip will not only cause a change in the oscillation amplitude but also change the resonant frequency and phase of the cantilever. The amplitude is used for the feedback and the vertical adjustments of the piezo scanner are recorded as a height image. Simultaneously, the phase changes are presented in the phase image, generally termed as topography. Different components of the sample exhibit different adhesive and mechanical properties and reflect different phase contrasts that allow compositional analysis of the materials. For a good phase contrast, larger tip force are in advantage, while minimization of this force reduces the contact area and facilitates high resolution imaging. Silicon probes are primarily used for tapping mode applications. The amplitude of the oscillation of cantilever decreases as it approaches the surface of the specimen as shown in figure 2a. This can be explained by observing the resonance behavior of the cantilever far away from the surface and close to the surface, which is represented in the black curve and the red curve respectively. When the cantilever moves close to the specimen surface, an additional restoring force acts on the cantilever and the tip sample interaction pushes the cantilever back. This can increase the spring constant, which manifests itself in a shift of the cantilever resonance frequency to higher values. In tapping mode, the cantilever is always excited at a fixed frequency that is chosen to be just below the free resonance frequency F0. Far away from the surface, the cantilever will oscillate with amplitude of A0. When the cantilever comes closer to the surface, the resonance curve shifts, but the cantilever is still excited with frequency F0. The resulting amplitude near the surface A1 is reduced from A0. It is important to know that the cantilever still does touch the surface, but only at the bottom swing of the cantilever vibration. This drop in amplitude can be used as the feedback parameter for AFM imaging, just like the cantilever deflection in the contact mode. only that in tapping mode, decreasing the set point value increases the force on the sample, while in contact mode, decreasing the set point decreases the force on the sample. Using the change in amplitude as a feedback parameter is called operating the AFM in amplitude modulation mode. One can also track the shift of the resonance frequency of the cantilever when it approaches the surface. That is called frequency modulated mode. The amplitude modulation mode or tapping mode is the most common way to operate the AFM. Cantilevers for tapping mode are stiffer than cantilever for contact mode to allow for a resonance frequency. Typical values for K is 40 Newton per meter and F0 in a range of 300 to 400 kilohertz. Now let us see the advantages and disadvantages of this mode. The advantages of this mode is that tapping mode allows high resolution of samples that are easily damaged and or loosely held to a surface. Second, it is a good for biological samples. It provides higher lateral resolution from 1 to 5 nanometer. It causes less damage to samples even with stiffer probes, and it eliminates a large part of permanent shearing force. The disadvantage of the tapping mode are difficult to produce image in liquid medium, and it is a slower scan speed. Phase imaging, a secondary imaging technique for tapping mode. Phase imaging is a powerful technique sensitive to specimen's surface stiffness or softness and adhesion between the tip and specimen surface, allowing the chemical mapping of the surface based on these materials differences. It monitors the phase lag between the signal that drives the cantilever to oscillate and the cantilever oscillation output signal. In tapping mode AFM, the cantilever is excited into resonance oscillation with a piezoelectric driver. As the sharp probe is brought into proximity with the specimen surface, it oscillates vertically near its mechanical resonance frequency. The amplitude of oscillation is reduced as the probe taps the surface, and this change in amplitude helps tracking the surface topography. The probe motion can be characterized by its phase relative to a driving oscillator. As the cantilever oscillates, it will exhibit a phase shift phi between the drive and the response, which is denoted by the equation d is equal to a sine of 2 pi f t plus phi, where d is the deflection, a is the amplitude, f is the frequency, t is the time, and phi is the phase shift. With any change in interaction between an oscillating cantilever and a sample, the resonance frequency of cantilever also shifts either towards lower frequencies for attractive forces or to higher frequencies for repulsive forces, and consequently the phase at a fixed frequency shifts. The phase signal changes as probe of the cantilever encounters regions of varied composition. However, the challenge with phase is that it shifts due to a convolution of multiple material properties such as adhesion, stiffness, which is modulus, dissipation, and viscoelasticity. Phase shifts are registered as bright and dark regions in phase images, comparable to the way height changes are indicated in height images. Phase detection images can be produced in any of the operational cantilever mode, such as tapping mode AFM, magnetic force microscopy, which is MFM, or electrostatic force microscopy EFM. The phase lag and change in amplitude is monitored simultaneously such that images of topography and material properties can be controlled, giving direct correlation between surface properties and topographies. The applications of phase imaging. It is useful in identifying contaminants, deposits, and discontinuous or defective thin films. It is used to analyze different components in composite materials. It can examine both organic and inorganic materials. It differentiates region of high and low surface adhesion or hardness. It is useful in mapping of magnetic and electrical properties with wide range implications in data storage and semiconductor industries. It is used to map variations in the surface properties such as elasticity, adhesion, and friction as it cause phase lag. The phase imaging usually complements lateral force microscopy or LFM and force modulation microscopy FMM, often providing additional information more rapidly, conveniently, and with higher resolution. It can generally achieve lateral resolution of 10 nanometer. The phase imaging is as fast and easy to use as tapping mode AFM, with all its benefits for imaging soft, adhesive, easily damaged, or loosely bound samples. The next is the non-contact mode. In this mode, the cantilever is held at a distance in the order of few tenths of angstroms away from the sample, and the probe tip causes the attractive forces to interact with the sample. The tip sample interaction is minimized. Working in this mode allows scanning the surface of the sample without influencing its shape by the tip sample forces. The cantilever for this mode are having high spring constant of 20 to 100 Newton per meter, so that it does not stick to the sample surface at small amplitudes. The cantilever oscillates near its resonant frequency, is nearly equal to 200 kHz, to improve sensitivity. The tips used for this mode are silicon probes. The advantages of these modes are it is low force of magnitude in 10 to 12 Newton is exerted on the sample surface. There is no damage caused to the soft samples, and it could be scanned with extended lifetime. But the disadvantages includes it has lower lateral resolution and it is limited by the tip sample separation. Slower scan speed to avoid contact with fluid layers, and the possibility of contaminant layer on surface can interfere with the oscillation, and it needs ultra high vacuum to have best imaging. So, the atomic interaction at different tip sample distances also noticed. The repulsion causes at very small tip sample distance at few angstroms. Very strong repulsive force appears between the tip and sample atoms. Its origin is the exchange interactions due to overlapping of the electronic orbitals at atomic distances. When this repulsive force is predominant, the tip and sample are considered to be in contact. The attractive van der Waals force causes polarization, interaction between atoms, and instantaneous polarization of an atom induces a polarization in nearby atoms and therefore an attractive interaction. The advantage of imaging modes are additional measurement modes, often in combination with special cantilevers, enable the measurement of sample properties beyond the topography. Examples are MFM and several electrical modes. Some of the modes depend on the detection of magnetic or electrical fields. Key in such measurements is to separate the short range van der Waals forces from the longer range electrical or magnetic forces. A lifting mechanism enables the probing of longer range electrical and magnetic forces and deconvoluting them from the short range van der Waals forces that are present during topographic image. Different kinds of AFM systems. First, let us see the lateral force mode LFM. The LFM signal, which is related to the change in the surface friction on a sample surface, measures the deflection of the cantilever in the horizontal direction and can be represented as the difference in the signals recorded in the right cell A plus B and the left cell C plus D. The frictional information is equal to A plus C signals minus the signals coming from B and D detectors. The schematic of lateral force microscopy LFM is given in this figure. The LFM measures lateral deflections or twistings of the cantilever that arise from forces on the cantilever parallel to the plane of the sample surface. It images variations in surface friction arising from inhomogeneity in surface material. Its imaging is also enhanced by edge deflection from the slope variations of surface features. This differences from the imaging of different materials by two sharp changes up or down at both sides. Force modulation microscopy, which is a secondary imaging technique. In AFM mode, the tip is scanned in contact with the sample and the Z feedback loop maintains a constant cantilever deflection as for constant force mode AFM. A periodic vertical oscillation signal is applied to either the tip of the sample, the amplitude of cantilever modulation that results from this applied signal varies according to the elastic properties of the sample. From the changes in the amplitude of cantilever modulation, the system generates a force modulation image, a map of the sample's elastic properties. The frequency of the applied signal is on the order of hundreds of kilohertz, which is faster than the raster scan rate, that is, the Z feedback loop set up to track the scanning. Under the same force, a stiff area on the sample deforms less than a soft area, that is, stiffer areas put up greater resistance to the cantilever's vertical oscillation and consequently cause greater bending of the cantilever. The variation in cantilever deflection amplitude at a frequency of modulation is a measure of the relative stiffness of the surface. Topographic information can be separated from local variations in the sample's elastic properties, and the two types of images can be collected simultaneously. Direct correlation between topographic structure and elastic properties. The magnetic force microscopy, or called MFM. The MFM is a phase imaging mode that uses AFM cantilevers with a thin magnetic coating in order to probe the magnetic field between a sample and a magnetized tip. This method is commonly used to image any materials with heterogeneous magnetic properties such as magnetic based hard drives. It can be operated in single, interlaced and dual scan line modes. Any of these modes require optimization of the height above the sample at which MFM image is collected. Now, the conductive AFM, or generally termed as CAFM, that here in this mode the electrical measurements are performed. The AFM can probe a wide variety of electrical properties of materials and surfaces. These methods operate either in static mode or dynamic mode, depending on the information being sought. Probing properties such as current, conductance, surface potential and capacitance are increasingly important in a number of applications, including research on semiconductors, solar and battery cells, conductive polymers and nanoelectronics. This is a static mode method where both the current distribution and topography of a surface are mapped simultaneously. It is similar to scanning tunneling microscopy, as in both modes a bias voltage is applied between tip and sample, and the tunneling current is measured between the two. However, the advantage of CAFM, which causes a conductive cantilever as opposed to a sharp metallic wire, is that it provides topography information and current information independently. Single point measurements that measure the current versus voltage curves can also be collected in this mode to probe the detailed electrical properties at a position. Then the piezoelectric force microscopy, generally termed as PFM. This static mode based method is geared towards the study of ferroelectric or piezoelectric materials, which are materials that respond mechanically to the application of an electric field. This mode measures topography simultaneously with mechanical response of the material when an electric voltage is applied with a conductive AFM tip. A sharp conductive AFM tip is brought into contact with the sample and an AC voltage is applied between the tip and sample. The sample will either expand or contract oscillatory due to this applied voltage. The sample motion is then tracked by the cantilever deflection, which is detected with a lock-in amplifier. The amplitude gives information on the piezoelectric tensor of the material, and the phase provides information on the polarization direction. Then comes the electrostatic force microscopy, or EFM. This mode is an electrical equivalent to MFM and operates in phase imaging mode. But now used for imaging variations in the electric field of the substrate. When scanning the tip lifted above the surface, typically only a few tenths of nanometers, a voltage is applied between tip and sample to create long-range electrostatic force. AFM images reveal information about surface potential and charge distribution from the phase image, with increasing magnitude of the potential difference between tip and sample. The resonance frequency drops, causing reduction in phase. Thus, a lower phase indicates larger absolute potential difference. This also means that the contrast can be varied with the applied voltage. The other one is Kelvin probe force microscopy or KPFM. This mode images the surface potential distribution of a sample without direct electrical contact between the tip and the sample. It operates in dynamic mode with either a single or dual pass step setup. In this single pass setup, the tip is closer to the sample, so there is higher sensitivity and resolution in the Kelvin force measurement. But the topography resolution may suffer. In the dual pass setup, the tip is farther away from the sample, resulting in lower sensitivity and resolution. But the topography can be sharper in KPFM. A combination of AC and DC voltage is applied to the cantilever, causing an oscillating electrostatic force between tip and sample. The resulting deflection oscillation is detected with a lock-in amplifier and minimized by the DC voltage. The DC voltage used is the local contact potential difference or CPD between tip and sample. Applications of KPFM include imaging the Kelvin potential or work function of a surface and measuring applied voltage differences between conductors. The other microscopy belongs to electrochemical AFM or EC-AFM. This mode enables AFM measurements while electrochemical reactions are taking place in electrolyte solutions on an electrode surface. Electrochemical reactions are processes in which electrons flow between solid electrodes and liquid electrolytes, accompanying a reduction reaction at the cathode and an oxidation reaction at anode. These reactions are widely studied in applications such as corrosion and photovoltaics. EC-AFM measurements enable monitoring the electrode structure during such reactions and establishing the relationship between the electrode structure or morphology and its electrochemical activity. As this mode occurs in aggressive liquid environments, excellent environmental control and protection of AFM electronics is necessary for effective imaging. So students, let us summarize what we have learned in this module. The AFM can generate an accurate topographic map of the surface features. There are three operational modes in AFM. First is contact AFM, second intermittent contact or tapping mode, third is the non-contact AFM mode. Using the basic principles and different modes of operation, various kinds of force microscopes are developed. Thank you.